All right. Well, good morning. Our next speaker is a firmware engineer who has plenty of experience working with consumer electronics like the Amazon Echo and IoT scooters. His present focus is on exploring smaller hardware and what it takes to get a product off the ground from scratch. His talk today will take us through the process of designing test fixtures and manufacturing. Please welcome to the Hackaday Super Conference stage, Kerry Scharfglass.
Hello. I think we had an oopsie. This is the thing that you think it is. Hi. So the thesis for this talk is relatively simple. It let me put things like this on a very large screen. The security stuff that you see in the news is the sexy hot vulns like differential power analysis and the Chinese government putting computers in your computers and people freezing the RAM in your laptop so that they can dump the TPM crypto keys and things like that. But that's not real. I mean, it's real, it really happens, but it probably doesn't matter to you. The problems that matter to you are probably more like you should use cipher block chaining on your symmetric cryptography, and maybe you should only do firmware updates through a cable instead of through the Bluetooth. So there's kind of what we're going to explore. Why you should maybe consider carrying, I guess. I'm a firmware engineer. I was working at a consulting company for a while and shipped a bunch of kind of firmware widgets. We mostly worked on consumer electronic things. Most of the rest of this talk is going to end up being examples from that. One of those companies is dead, but I swear that's not related to my firmware. That was someone else's problem. So some more caveats. This is probably mostly relevant for bare metal kind of microcontroller type complexity, or maybe like a real-time operating system. Maybe less relevant for it's a full Windows computer. But then again, it turns out it's actually not really a technical problem, I might argue. So that level of complexity doesn't necessarily matter. The other caveat is if you're building payment processing hardware, you shouldn't be learning about security from a guy on a stage somewhere. You should talk to a professional. But I think that expectation is probably appropriately set already. So this is the whole talk, basically in this one slide, which is that you should think about security at all when you're building a product. That's it. That's fine. You can. That's it. I can put the mic back and we can end the talk now. Thank you. If we wanted to break that down a little bit, the basic process for building a product is kind of in the shape of you kind of like define the product a little bit, and then you iterate a bunch, and you do some prototyping, and you do some manufacturing ramp, and you ship the widget. So at all of those points, you want to do this cool thing called threat modeling, which we're going to talk about more in a moment, where you kind of figure out what problems could exist and figure out what you're going to bother solving and figure out what you're not going to bother solving because it doesn't matter. And that's kind of a continuous process once you've figured out what the product actually does. So what is threat modeling? Threat modeling is the process of sort of thinking like an attacker and figuring out all the different ways your product can be broken and the effect of breaking it in those different ways. So there are a bunch of different things that feed into it. And I'm going to disgorge a bunch of bulleted lists, which will be less useful than the following examples, but I think they'll help kind of contextualize things. So there are a bunch of questions you will need to ask. This is a random small list of them. Who's buying the product? What is the thing supposed to do? You kind of end up identifying what possible problems can exist and then identifying what risks are acceptable, what sorts of failures you don't care about and are not worth fixing, and then you probably want to fix the other things you've identified that you do care about. Okay, things that you can think about when you're kind of thinking about how to do some threat modeling stuff. What kinds of prerequisites are necessary for your product to be broken into or attacked? So do you need to be on the same network? Last week or the week before, there were some people who published a research paper using lasers to directly excite MEMS microphones in smart home speakers. So it's like, you don't have to be physically close by, you don't have to be on the same local network, but you do need a line of sight and a telescope, probably. Could you do it remotely? Is it connected to the internet? Do you need physical access? Can you have momentary physical access where you plug a flash drive into an ATM? Or do you need extended physical access where you can rip the thing apart and put it back together? You can kind of break down attackers into this unitless graph. It goes up and to the right, so profits are good. There's like the casual, I'm not paying attention to your product, I'm just looking for things with this port open type attacker. And then there's the like, I'm gonna pay a little attention, but my whole life's goal is not breaking into your thing. Then there's like, my life's goal is breaking into your thing. And then there's the times 1,000 version, which is like, the government wants to make sure they get into your house and they're gonna do whatever they need. They can use whatever resources they need to be able to do that. No one should care about that. Again, if you're building satellites for the government, you care about nation state actors, but this isn't, you're not learning from this talk in that way. Dedicated attackers, maybe if you're building a high profile thing, if you're like Nintendo and you want to make sure people can't root the switch, like, okay, maybe that's sort of like a dedicated attacker. Most of the time, the thing you actually want to care about, the bar you actually need to hit, isn't someone trying to wreck your product. It's like someone kind of casually bumping into it and knocking it over because you've done nothing at all, which is the like casually looking for vulnerabilities and the like child with squirt gun level of, this is actually an immediately relevant example, which will come up later. Okay, so what are some kinds of harm that maybe a person could do if they break your thing? They could cause fraud. Either they could cause fraud to you by like, getting something for free. They could cause fraud to others by causing them to be billed for something or impersonating them or something like that. They could hurt themselves, physically hurt themselves. They could physically hurt someone else. Maybe it's possible that they can like upload their own firmware, but all it would do is brick their own device. Okay, so that's like harming themselves. They could break your infrastructure if they can use your product as a beachhead to like climb back up. There's lots of different possible ways that they can cause damage. So you can kind of put it in like a hierarchy of oopsies. So there's like the oops, they hurt themselves, oops, they hurt other people, or they hurt you, or oops, they've harmed everything. More fire emojis is bad. Okay, so this was originally going to be an even longer list of random technical stuff, but that's not super engaging. So I think it'll be more interesting to talk about sort of examples of like threat modeling that I've done and the problems that we identified and the ways that we chose to mitigate those things. So the 3 example devices are a weird medical training device, like an IoT deadbolt for your home, and one of those IoT dockless electric scooters that you've probably seen strewn around the sidewalk somewhere. All the examples kind of have the same format. There's like what the product is, what the product's goals are, which is a hierarchical list, and then what the risks were and what were mitigated. So first example is this medical training device. Unfortunately, I'm not going to show you the exterior because that would make it much easier to figure out what it is. These are FCC photos though. It's a little battery-powered Bluetooth device. It was an IoT syringe, sort of. Find me later and I can explain what it was actually for. It was a very strange device which had this super cool like rigid flex PCBA assembly. It has a very specific use case. It's used for this one particular type of training and nothing else. It's designed to be used with a very elaborate setup in a training center, not at home. It has a very small battery. It's very, very limited in scope. So the product goals are like, be good at doing this training. It's a single purpose device. So what are the risks? There really aren't. This is the sort of product where security things were not a super relevant concern. You could take it. Okay, that's not really I guess you could come up with some crazy DRM style. You can only use it while you're in the building scheme, but like, okay, so you could steal it. You could break it, physically snap it in half. You could update the firmware to make it do something else. The point is this device is basically useless. It does this one thing. It has no other purpose, and it would be really hard to even force it to do some other things. The only kind of relevant bit would be maybe firmware replacement. There are a lot of games you can play to try to prevent someone with physical access from being able to update firmware or open up a development console or something. You can like pot it in epoxy, and you can lock down the like programming headers and stuff like that. You can authenticate firmware updates. You can authenticate and encrypt firmware updates. The only thing that we did was we made it has a Bluetooth radio, but you could only update it over USB. But that was really an engineering decision because we didn't want to spend the time to do OTA over Bluetooth. It has pleasant security effects, but that's it. Also, the FCC labeled this the printed slurkit board, which is why this is great. Okay, that example, very simple, kind of no security stuff. This is an IoT deadbolt. It's not super obvious from this picture, but so that the product is this bit over here and that over there, and then the the little tongue thing. This was a really hilariously, unbelievably mechanically complicated product and electrically complicated product with one really big processor, the same one in some of the high-end teensies, like 160 megahertz, Cortex M4, whatever, and two other CPUs for doing radio stuff and a radar and like all sorts of crazy things. It's a deadbolt. It replaces the deadbolt in your house. Unlike something like an August lock, which goes over your normal lock, this does not. This entirely replaces your normal lock. So this is the like sole governor of access through whatever that point is that it's installed. So it's very sensitive in certain ways. It's battery powered. It actually has multiple batteries as like a backup. It has Wi-Fi and Bluetooth radios. It connects to your phone. You can share access to all sorts of exotic things. So product goals are like, if it fails catastrophically, it is absolutely possible that you would be prevented from getting into your house. So like, do not allow that to happen under any circumstances. And then the follow-up is like, be really great. It was very expensive because it was very complicated. So one of the ways to justify that is like making it really good. So it needs to like be really smooth. Okay, so like it has its own network connection. You get physical access. Not only do you get physical access like over a limited time, you get long-term physical access. Someone can just show up at the door of your house and then they have access until someone tells them to leave. If you're using it to Airbnb, a stranger has unrestricted physical access that it looks like they're supposed to have. They can totally remove it from your door and do whatever they want to it and put it back together. Like the most unrestricted physical access you can possibly imagine. So there are a lot of risks. There are a bunch of privacy implications because it has a lot of sensors in it, and you could use it to tell when someone is home or not home. You could use it to tell when someone is home and near the door and the lights were off. You can like all sorts of interesting things. It's designed to be used to allow you to give access to people, so that's a thing. If you can like on the exterior, you can actually grab it and rotate it and enter like combo lock style pin codes. So if you can like inject a pin code in there, you could use that to get into a house. If you can reach in and just ask it to unlock, you could use that to get into a house. There are a million ways you can deny access through it. If it bricks due to a bad update, then that's it. You can't get into your house. If the battery is dead, you can't get into your house. If it can't connect to certain kinds of network control, that could be hard. If you can make it break itself, which it is mechanically capable of doing, then you can't get into your house or out of your house. There are like a million different ways. So I cannot take credit for all this stuff. This was a project which existed before I got there. A lot of engineering work had been done before I got there, so I did some of this, but not all of it. We mitigated, I think, a reasonable number of things. A lot of that was sort of as an artifact of the architecture of the product. So there are a bunch of just quickly going through things to prevent access. There are a lot of electronics in it. The electronics were physically located on the interior of the lock for the most part. So if you shattered the glass on the outside and got to the PCBA that was behind it, there was not really a lot there that you could exploit. It was designed with hardened steel, so you could, and this is testing they did, they like sledgehammered it with like a giant test rig to make sure that if you sledgehammered it, you couldn't sledgehammer it off the door, basically. Or if you did, it wouldn't cause the house to become unlocked. There's a whole like test regime for lock hardness and stuff which they applied. The rate limits for some of the messaging stuff. There was a mechanical release on the interior that didn't require any battery power or the lock to be working at all, so you could get out even if it was totally dead. There was a secondary battery which is used to allow you to get in if the primary battery is totally dead, and it only wakes up when you physically press a button which requires you to physically be at the lock, so even if you could remotely reach in and do something to cause it to die, that battery would still not be harmed. At the end of the day, though, it's still, all the things I said before, you're still giving potentially unrestricted physical access to this thing. So you can rip it apart and install a hardware implant. I don't see Joe Fitz here, but he can tell us all about that. At some point, it was just not worth, it was not reasonable to continue mitigating things. Okay, so pin code stuff. It had a serial console. We turned that off. This is like the most obvious things. We were using a Kinetis part, which has these really cool magic bytes you could write in Flash, which is sort of like soft fuse the JTAG and the SWD off, so you didn't have to do it as a manufacturing step that was irreversible. So you could later come and basically play a magic certificate into it, and it would like turn its debug headers back on. But normally in the field, you couldn't plug into it and dump anything out of it. It also had a big table of pin codes and a big table of like timestamps and things which governed when certain pin codes were active and when certain people could have access and things like that. So there was more of that data than we wanted to store in the main flash of the part, both in terms of flash wear, so that we didn't wear the part out, and also because there was just like physically a lot of it. So we stored it in an external flash chip. There's sort of a risk when you do that, though. When you take the thing apart, it's not that hard to like look at the parts on the PCBA and try to find like a NOR flash and then plug into it and just speak SPI to it and get it to dump all of its secrets. So we had to encrypt all of that. So we sort of treated the main microcontroller's flash as the like root of trust. We considered it to be inviolate. What's the word? Sealed, perfectly sealed. Once we'd done all the other flash lockdown stuff, we sort of got it to the point where you would have to like decap the part and inspect it to get data out of it, which we determined was acceptable. Again, if you think of the like curve of attacker hardness, someone kind of randomly, casually trying to break into this thing or even leave a hardware implant is not going to be decapping the ICs to try to read out the flash. So that was acceptable. So we used symmetric crypto, AES specifically, which was accelerated by our CPU. The main crypto key was generated in the main CPU in the lock and never at any point left. It just happened at the factory silently, and then that was used to transparently encrypt all the stuff on the part. The 3-second interesting explanation of cryptography stuff. So there's symmetric, and again, I am not a security expert, so symmetric crypto, asymmetric crypto, they're useful for different things. Symmetric crypto is nice because it's easy to find microcontrollers and stuff that have hardware support for accelerating it. It's great for encrypting like all the blocks in a flash device, things like that. Asymmetric crypto is cool because you can do things like construct public-private key pairs, which let you validate that messages came from who you expect, and then certificate chains, which allow you to certify that like this message comes from someone you trust, comes from someone you trust, comes from someone you trust. So it sort of ends up being a wrapper of a couple layers of things. OTA, this is a device with a bunch of firmware. The firmware is pretty complicated, so it could be updated. You could OTA it. We decided that we weren't going to do any Wi-Fi OTA. The only way to OTA it was over Bluetooth because that guaranteed that you were physically close to the device. And more than forcing Bluetooth, the lock only allowed you to pour updates into it when it was unlocked and the door was open. So we could actually tell where the door was relative to the strike plate on the frame. So we could tell if it was totally, we could tell if the door was positioned closed or positioned partially closed or open. So this way, if an update really did go catastrophically wrong and the lock totally died, we could guarantee that you were not going to be in a state where you were locked inside your house. Even there was the mechanical release and everything, but as an additional layer, we could like say that strongly, and that was good. We did asymmetric and symmetric crypto, so we authenticated that the updates were from the backend infrastructure, and then we encrypted the updates themselves. The process for handling those certificates was very careful. They were hand delivered to the factory, and only a limited number of people had access to the like rootmost key that was used to create all the successive keys below that. So there's like a lot of physical security stuff related to that. Remote access and being compelled to unlock the house. There was a lot of very elaborate crypto stuff between the individual lock and the individual app on your phone that allowed messages to be encrypted end-to-end between the lock and whatever device you're using to unlock it, so none of the backend infrastructure could see into it. It's worth noting, though, that you can make a bunch of really strong statements about being end-to-end encrypted and not be lying, but if the device is designed to accept firmware updates from whatever company, and you can't inspect the firmware updates, or you choose not to, it might be end-to-end encrypted, but nothing prevents the company from pushing a firmware image down, which either makes it not be end-to-end encrypted, or just inspects the messages when they come out of the crypto pipe. So, like, if someone really did force the company to unlock a lock, there was not something a customer could do to guarantee that, like, that didn't happen. Okay. So, on to devices which can, sorry, before I forget, I mentioned the kid with a squirt gun. So this lock is waterproof on the outside because it would be really bad if a kid with a squirt gun squirted the lock and that killed it. That would be a really disappointing form of denial of access. Okay, so IoT electric scooters, these are random scooters I do not mean to imply that these are or are not scooters that I worked on. I did work on one of the ones that you see around, though. So the premise of these devices, for background information, is they're on the side of the road. You usually like scan a QR code, and the scooter will unlock and disengage some sort of software brake, and then you can ride the scooter around. They're powered. They have a big battery. They're fun. When you're done using them, you usually pay by minute plus some flat fare. You like lock them up and check out of them in the app, and they get returned to the fleet. You can like find them on your phone. The relevant one that I worked on for this was based on the ES4 chassis, which is made by a company called Ninebot Segway, which is an exceptionally common chassis. Ninebot is the Chinese company that bought the Segway brand. They build the little Segway thing. They built almost all of the scooters that you see on the street. These particularly are ES4s. They move really fast. They have really big batteries. They're cool, unlike the medical training device, which is not cool. These are obviously useful because you look at this and you're like, yeah, I would love a cool scooter, unlike the medical training device, which no one is like, oh yeah, syringe for simulated medical training. No one cares about that. But these are like cool. They have Wi-Fi radios, they have cell radios, they have Bluetooth, they have GPS, there's like all sorts of good stuff, and they're designed to be shared between users. So product goals, again, do not harm the user. These are actually dangerous in like a very tangible, conspicuous way. Provide the best user experience because they're all basically priced the same. It's all like $1 plus 5 cents a minute or 15 cents a minute or something. And then maybe make money, but no. The company that did this, and all of the companies as far as I can tell don't, making money is like a very tertiary sort of goal. That'll come up later in how we mitigated some problems, so I swear it's relevant. Okay, so there's like a lot of possible harms here. Product is cool. Everyone gets physical access, and unlike the lock, I mean, if someone was like standing outside of your house for 4 hours with a bunch of tools playing with your door lock, maybe a neighbor would care. These are like recreationally trashed. They're designed so that you can pick them up and walk around with them. There's like no one cares at all. People will laugh and take funny videos of you playing with them. So like the most unattended physical access, no contract or agreement of any kind. You can hurt yourself, you can hurt others, you can remotely hurt others because it's a giant electrically powered wheeled vehicle with a motor. So there's like all the good fire emojis in here. Okay, so the set of stuff that we identified and tried to fix. There's a bunch of safety concerns. They have brakes. The brakes can fail. You can have throttle failures, which can either be bad because you accelerate forever or bad because you're in the middle of an intersection on a hill and suddenly you can't get out of the intersection. There's a bunch of privacy implications because it has a radio and a GPS and it knows who's on it, and it has a Bluetooth radio. You can like look around and see what's near it. There's all sorts of possible fraud. There's like getting free access to rides, stealing the scooter. All sorts of great stuff. Do not have service. You can destroy the scooter during an update. You can rip the brain out of the scooter and replace it. You can rip the brain out of the scooter and not replace it and just take the scooter. You can destroy the scooter recreationally. You can cut the brake lines. You can pull the wheels off it. You can pop the tires, though I don't think anyone's stupid enough to have pneumatic tires at this point. So we mitigated some of this and not others. I'm not going to talk about the privacy stuff. That, I think, for our purposes, is mostly a back-end concern. The short answer for privacy is all of the communication went through the cell radio directly to the company backend. It was wrapped in crypto. Brake failure, throttle control and stuff, we took a lot of steps to mitigate both risks in terms of product safety and risks in terms of like security vulnerability related product safety. There's no mitigation for the user being an idiot. Fraud and theft, we mitigated some of. We didn't mitigate others because at the end of the day, it's going to be sitting on the road and people can pick it up and use it. So safe OTAs, we didn't. They had to be updated. We had to ship them like months before we thought we were done with them. So like they had to be updated. They have Wi-Fi radios, they have cell radios. There's no technical reason why you can't OTA them. We just didn't, because that was a big can of worms in terms of like reliability and recovery, and a big can of worms in terms of engineering complexity, and we like weren't going to touch any of that. So these devices are interesting because the companies that produce them do a bunch of fleet management, and it is, I assume all of them do this. They either pay people or they like employ people who drive vans who go and physically go to the scooters and pick them up every night and inspect them to make sure that they're still mechanically sound, and take them to a warehouse, and maybe they charge them or they're paying someone else to charge them, things like that. So instead of doing OTAs over the air, we did OTAs by having the like fleet, there's a word, shoot, I don't remember the name of those employees. But by having the employees whose job it was to like service the scooters, the techs, I guess, update it themselves by physically like opening it and plugging into it. And that allowed us to basically use money to totally eliminate an entire class of problems. So that was kind of an interesting, they were already going to do it. It was like an interesting thing we could exploit. And we exploited it in a couple times. Again, I mentioned the scooters were physically inspected before they were put back into the field. So if there was something obviously like attached to the PCBA, the people inspecting it would know that. You can play a lot of games to make it either tamper evident or tamper resistant, either by potting the whole thing in epoxy, which is my favorite solution to all problems, or including really elaborate anti-tamper like photo sensors to measure if the case has been opened and send a message, or like distance sensors and things to see if the case has physically come off the top. Hall effect sensors and embedded magnets. You can do like wire meshes embedded in the plastic that detect if they're broken. You can do all this stuff. That was totally not worth it. Again, company is expecting that these are consumable. They're expecting that these scooters are going to disappear and they're going to require serious service. So we didn't care. That was all totally acceptable. There was just a number, which was the number of scooters the company was expecting to lose, and that was fine. That was it. We like didn't. That was the end of that path. We didn't have to mitigate anymore. I mentioned all the comm stuff went through the cell radio. We can talk about spoofing cell networks. That was not something we were worried about. All the handshaking stuff all happened through sign messaging with the back end, whatever, out of scope for this. Brake and throttle. So these scooters are interesting for a variety of reasons. This on the left is a Xiaomi M365. The M365 is made by Ninebot Segway and white labeled by Xiaomi. In this case, I guess literally white labeled. The M365 is a great scooter and it's really well built. It has some interesting traits. One of them is that it has a real disc brake. So it's like a real, honest to goodness disc brake with a cable, which can be cut, which is unfortunate, but that goes to like a mechanical brake handle at the top. So you're riding the scooter, and you have a throttle, which does throttle, and you have a brake, and the brake mechanically engages the caliper in the back and everything. The ES4 does not. The ES4 has one motor in the front, and it has like the kick scooter stomp brake in the back, but it has a throttle and the brake up top. The throttle works like a throttle. The brake doesn't. The brake basically turns the regen way up. So it doesn't actually have a physical mechanical brake that you can rely on. And that is really, really scary. It's scary because we observed a bunch of these things destroy themselves when you rode them down a tall hill and braked the whole time and you weighed more than like 100 pounds. We had motors literally like melt apart in the wheel. But it's also scary because if you're going down a hill and you're about to hit an intersection, you need to stop. You're going to hit the brake, and the brake will hopefully work. You're not going to remember to hit the like stomp brake. You're going to freak out and probably ditch, and that's really, really scary from a product safety perspective. So again, we solved this partially with the application of money. There were people who physically inspected all these scooters every night before they went back out, so they could physically look at the scooter and see if like the brake was still attached and would probably still work. They emitted a bunch of health metrics related to how many miles they'd had put on them, how many charge cycles, things like that. The real mitigation though was that we put a whole second microcontroller on the board, and the second microcontroller was the only responsible party for all the throttle and brake stuff. So there's actually, the way these scooters work, there are two controllers on them. So there's a sort of an ECU on the bottom that does battery charge stuff, as well as it is the speed control. It does motor control stuff, and it talks to a micro up at the top. The ES4 works the same way. All the electronics and the battery and stuff is in the stem, motors in the bottom, and then there's a second board in the very top. So we replaced those, the brain, which is what normally has the Bluetooth radio and the UI and things. So in our replacement, we have the big microcontroller with the cell radio and everything, and then we had a totally separate microcontroller, which was connected to the main microcontroller through a UART, which spoke a very narrow set of comm stuff that we defined, and that's it. It couldn't be updated, and you couldn't tell it what throttle or brake position to set, but its whole job was to read the analog throttle and brake signals and send those messages down to the ECU. So if something happened to the main micro, if it got wedged in a crazy way, if some network thing timed out and somehow a thread got jammed, Something goes totally crazy. That was fine. You could still continue riding it. There was a heartbeat, so it could detect if one of the micros got totally hung and was no longer responsive. There was some pretty elaborate sort of sanity checking that happened from the ADCs. So we were detecting things like wires being pinched and shorted, ADCs being disconnected, and thus like the current draw falling off, all sorts of things like that. So that physically separated like remote access to the throttle and the brake, and also improved safety stuff. Theft, this is a fun side effect. So I pulled this picture because it's just a picture of the top of the scooter. That picture came from this cool Amazon page. There's a weird mixture of keywords here. Headstock, handlebar, firmware handle kit for ES2 handle replacement part. It's like, okay, so it's these plastic parts, pictures of plastic parts. That's cool. If you look down, there's this question. Why not compatible with shared scooters? Hi, the headstock handlebar firmware is compatible with shared scooters like Bird, Lime, Lift, and Skip. So when these companies deploy these scooters, there's some amount of customization that goes on, but not that much. And it turns out, in a lot of cases, you can take the scooter and you can rip their brain off it, and you can buy a totally off-the-shelf, either manufacturer like OEM part or replacement drop-in part, and just reinstall that in the top of the scooter exactly where it came from. And like magic, the Bird scooter becomes your scooter because they didn't replace any of the other stuff. It's like theft is like obviously a real thing. You can go to Amazon and buy for $7 an entire replacement like PCBA button assembly thing that you can stick into one of these scooters to turn it back into a dumb scooter. There is like real demand for this kind of product. I don't know if product is the right word. This is an example of why the theft stuff was not, it was like a business case to write down. It was not something that we were going to be able to effectively mitigate. Because these were people who were relatively targeted in their desire to use the scooter for their own purposes. So I guess the point here is that wasn't, there were technical moments, but it was not really, I would argue it's more of a social problem than it is a technical problem to hit a reasonable bar, not to be NSA proof. That's a whole nother can of worms. But to cross the threshold where it's hard for someone to casually say, brick your entire fleet of scooters because they can just OTA them because you didn't bother checking to see if the updates were coming from someone you trust, and you didn't bother making sure the updates were coming from someone who was physically nearby. So like step 0 is pay attention. Turns out if you care about making security stuff better, wow, incredible. You'll do better than people who don't care at all. And then the process is identify problems that might exist, figure out what the business is willing to accept in terms of risk and damage, and then don't fix anything else. Like fix the things that you care about. Do not spend energy fixing things you don't care about. So I'm Kerry, and this has been Basic Device Security for Basic Needs. Thanks.